All right, liberal arts. In this video, we're covering functions this time. So intro to functions. So in class, I kind of made you write out these definitions. We also made some of these tables and graphs kind of sketched out together. But for the purposes of this video, just to make it go by a little quicker, I've already made those. And I'll just talk you through them to make sure you understand what they all are. So spoilers, you can already see some answers to questions, essentially. So what is a function? So in class, I made you guys write this out, but a function, a formal definition is it's a relation in which each input value has exactly one unique output value. Or an informal definition is each x value has exactly one y value. Now, that does not go the other way around. It's not saying that each y value has exactly one x, okay? So it's not each y has exactly one x value, right? It's not saying that. It's kind of, you might think of it that it goes both ways, but it really doesn't. It's only saying that each x value has exactly one y value. It's not saying that each y value has to have exactly one x value. So that's very easy because it's to get confused, because a lot of times people think that this goes both ways, but it doesn't. Okay, it's listed in this order for a reason. Each x value has exactly one y value. So when you look at your tables that we've made in class here, you'll notice that for each x value, for example, 2, each x value, this x value here, 2, has one y value of -3. You don't see 2 anywhere else on this chart going to any other number, right? Same thing with 5. 5 only goes to one y value, or only has one y value attached to it of -5. 9 has only one y value attached to it, -1. 11 and 16, again, both have one y value attached to them. So it's considered a function because each of the x values pairs up with one of the y's. You can notice that as well in the bottom part of this table, is that each of these x values has one y that it goes to. So -3 has one y value of 5. -2 has one y value of 2. -1 has one y value of 1. 0 has one y value of 2. And 1 has a y value of 5. So each of the x values has one y value. But you'll notice, of course, that 2 of these x values have y's of 5, and 2 of them have y's of 2s. And this is okay, because remember, it's not each y value. We just wrote this before, and I erased it. Should have left it up there. Remember, it says it's not each y value has one x, right? It doesn't have to be that each y value has to have one x. So you'll notice that the 5s here for the y, they have 2 different x values, right? -3 and 1. But that's okay. There's nothing wrong with that. There's nothing wrong with having multiple y values that go to different x's. That is totally fine. You just don't need to have it the other way around. You can't have x values go to different y's. So you'll see that in the not function section to kind of illustrate my point. You'll notice in the not functions, basically I'll just point out the thing that you really need to focus on is the x value of 2. This x value of 2 goes to -3, and this x value of 2 goes to +3. So you'll notice that the x value of 2 has a y value of -3 and +3. But remember, each x value has exactly one y value, but not this one, because this x value, the x value of 2, has 2 y values. It has a y value of -3 and a +3. So that's considered not a function. Okay, so it's okay for the y values to have different x's. That's fine, nothing wrong with that. But you can't have x's, right, with different y values. That's where you really kind of have to wrap your head around that. You'll notice in this last chart that -2 is the culprit here. -2 goes to 12 and to 19. So the x value of -2, right, goes to 2 different y values of 12 and 19, and that's a no-go. Okay, you can't have an x value with more than one y value. Each x value, I can't emphasize that enough, has one y value. Okay. All right. So how can we tell if a function is a function without looking at a table? It's very easy to tell by looking at a table because you're looking for the x values that have different y values. That's how you can tell by looking at a table. But how do you tell if it's a graph? Okay, well, let me zoom in on these. Something called the vertical line test. So let you pause the screen or let's read it real quick. The vertical line test can tell you whether something is a function or not. So if you draw a vertical line through any part of the function and the vertical line crosses the function more than once, it fails the vertical line test. So I'll show you some functions real quick, and then I'll scroll over to show you some not functions. So the vertical line test works like this. You draw a vertical line, which is, remember, vertical is straight up and down, okay? It's not slanted at all. It's not sideways, okay? It's straight up and down, right? Your vertical line test is supposed to only hit your graph. So you notice this graph here that's in blue that I just covered up, right? It's only hitting it in one place. And in this case, it is, right? It doesn't hit, my vertical line does not hit that line any more than just once. And that happens no matter where I draw the vertical line. It's going to hit that function, that line on my graph only once, no matter where I go. That's the same case over here. So if I draw a vertical line, only hits it once there, only hitting it once there, right? No matter where I draw a vertical line, it's only going to hit this graph in one spot. Okay, same thing down on these two. So vertical line here, again, I've only hit the graph here. Vertical line here, I've only hit the graph there. Vertical line here, I only hit the graph there. Only one time. So no matter where I draw a vertical line, I only hit the graph once. Same thing here. Vertical line, hit the graph only once. Vertical line hits the graph only once. Vertical line hits the graph only once. Those are all passing the vertical line test. Now, these do not pass the vertical line test, okay? You'll notice the circle one, when I draw my vertical line, I hit the graph once and then twice, right? I'm hitting it in two different locations on my vertical line. That's failed. That is not a function. You can see it as well in this case. I hit the function here and here, right? More than once. I hit it twice. So therefore, it fails vertical line test. It could be anywhere on the function, any particular spot. So you'll notice this function here, a vertical line would pass like there because that vertical line would only hit the graph one time. But it has to, if the vertical line could fail anywhere, then it's not a function. You'll notice that the vertical line test fails, of course, right here. Fails the vertical line test there because you're hitting the graph once, twice, three times, and therefore it's failing. It cannot do that at all. Has to pass the vertical line test everywhere to be a function. If it fails in just one spot, then it's no longer a function. It would also fail over here as well. It would fail if I drew the vertical line test. If I can draw a straight line up and down, it's kind of tough. But anyway, you get my idea. It would fail here because that vertical line would go through another 3 points on the graph. And then you can see our last one as well. Definitely fails the vertical line test there. So you can draw the vertical line anywhere. It doesn't have to be where I'm drawing it, but you can tell I'm just drawing it in multiple places just to kind of prove the point, right? It fails vertical line test. It hits the function twice. So that's how you can tell whether it passes or fails the vertical line test. So in class, we kind of just sketched these out ourselves, but there we go. But yeah, there I just already had the graphs determined. So scenarios. Determine whether the scenario given represents a function or not. So our first scenario is a baseball is hit at a Little League game. The coach relates the time the ball was in the air to the ball's distance. So consider time as your x and then distance as your y. So if it's not a function, then it would be at the same x value, it would have different y's. But is it possible, because there's time here, is it possible that any particular time, so like 2 seconds, let's say, at any particular time, it would be at more than one height? Or I'm sorry, not height, distance? The case is no, right? To not be a function would say that at 2 seconds, the ball was at 3 feet away and then also 10 feet away. But if it's at 2 seconds, the ball can't be in two different places at that same exact time, right? That's not possible. The ball's only ever going to be in one place at a specific time. So this would be a function. The only way it wouldn't be a function is if you could have the ball in two different distances at the same x value at the same time. So at 2 seconds, the ball's only going to be in one place. The ball can't be in two places at that time or at any time. So yes, this one passes. This one would be a function. B, Tasha goes grocery shopping for her family. She relates the price of each item with the item itself. So price as our x value, and then item as our y. Now, this isn't really a quantity, but you get the idea. Now, this one is also a function. Yes, and let me explain why. The reason is that at each... Wait, hold on. Actually, hold on a second. Hold on. Let me think about that again. She relates the price of each item with the item itself. Actually, you can argue that this would not be, because let's say I had the price of $2, right? Well, there could be more than one item that's $2, right? You can have deodorant that's $2. You could have toothpaste that's $2. So the price of the item is not limited to the item itself. It would be a function if it were the other way around. If the item was the x and the price was the y, then it would be a function, because each item, for example, let's talk about toothpaste, right, is going to cost that amount of money. You're not going to have the same brand of toothpaste, right? I'm talking about the same exact item. I know it's different brands, but you pick up the same item, right? It's always going to be that one price. No one's going to walk in the store and buy a 2-liter Coke for $1, and then the next person comes in and buys it for $2, right? That 2-liter Coke is going to be the same price. So if it were the other way around, it would have been a function, but not if it's this way, because the price could vary, or it could be the same for different number of items. So kind of tricky to explain that one, but I hope I get the point across. C, a wrestling tournament is going on at school. The contestant's age is related to their weight. So let's consider age as x and weights as y. Now, this one is not a function. For example, we could have somebody who's 15 years old, and people that are 15 years old are not going to be exactly the same way. You might have a 15-year-old that's 120 pounds. You might have a 15-year-old that's 150 pounds, right? So it wouldn't be a function to relate age to weight, because you could have people of the same age have different weights. All right, but that one is those are very tricky. You really have to put some thought into those. X-intercept, the place where the function crosses the x-axis. So these are just definitions again that we wrote down in class. X-intercept, the place where the function crosses the x-axis. Note, y is always 0 for the x-intercept. And y-intercept, the place where the function crosses the y-axis. Note, x is always 0 for the y-intercept. And then lastly, solution to a function. A solution is typically when you're asked to find the solution to a function. If you ever see a problem that says solve this function or solve whatever, it's meaning find the function's x-intercepts. Okay, x-intercepts are often known as the solutions to a problem. So when it says solution, find the solution, or ask to solve, it's really asking you to find the x-intercepts. So just something to keep in mind as we move forward. And then lastly, this is one we actually kind of did in class. Sketching a graph and then emphasizing the x and y intercepts as well in the solution. So if I draw a graph here, let me draw one. It's going to be kind of a rough sketch, but it'll be all right. Okay, there's a graph for you. Okay, x-intercepts or its solutions would be, and to the best of my ability, -3, +3. Those would be the x-intercepts. The y-intercepts would be, or just 1. There's only ever one y-intercept if it's a function, which would be 2, right? So solutions would be -3 and +3. There's a lot more about these graphs that we're going to talk about in the next video, as far as increasing goes, decreasing, domain, range, things like that. So we'll save that for the next one. I'll see you guys then. Later.